All right, so in this video, I am going to go over section 10.1, which is approximating functions with polynomials. So this is what the idea of constructing a n-degree Taylor polynomial, which can be used to approximate a function near a particular value. So I'll go over one where you can actually use this polynomial to approximate a value, and then I'll actually do another example, which is from the worksheet, where you find the nth degree kind of in general. So first, let's look at the question here. It says, approximate the value, the square root of 1.06. So, I mean, all of us probably have to use a calculator to actually get the exact value of this thing. But we can actually use a Taylor polynomial. And in this case, I want to use the third degree Taylor polynomial to approximate this value. So the first thing we want to notice is, right, this number 1.06 is close to 1, right? It's only 0.06 away. So I'm going to find the approximating polynomial centered at a equals 1, because this this number is near that value. So the theorem says essentially, right, f of x is approximately equal to the nth degree Taylor polynomial, and what that polynomial is at a would be k equals 0 to n, of the case derivative evaluated at the point 1 divided by k factorial, right, times x minus 1 to the k. So if I want to find the third degree, the first term of this would just be f of 1. The second term is f prime of 1 times x minus 1. The third term is f double prime of 1 over 2 factorial times x minus 1 squared. And then the third and final term would be the third derivative of 1 over 3 factorial times x minus 1 cubed. Okay, so there's essentially 4 things I need to find, right? This thing, this thing, and this thing. Once I have those 3 coefficients, that's what they are, the Taylor coefficients, I can then plug in the value 1.06 into this function, and I'll get my approximation. So what would be, so f of x, that's the function, the square root of x. So clearly, I'm going to write this as x to the 1/2 right now, because I know I'm going to have to do the derivative, and it'll be easier to do the derivative if it's written as a power function. So f of 1, that would just be the square root of 1, right, which is 1. So I'll just box the first term there. It's just 1. So f prime of x, right, that would be 1/2 x to the negative 1/2. So f prime of 1 would be 1/2 times 1 to the negative 1/2, which is 1/2. Okay, continuing on, we have f double prime of x. That would be negative 1/4 x to the negative 3/2 using the power rule. And f double prime of 1 then would be negative 1/4. 1 to the negative 3/2, which is negative 1/4. And let's see, f triple prime of x, that would be positive 3/8 x to the negative 5/2. So f triple prime of 1 would be 3/8 times 1 to the negative 5/2, which gives me 3/8. Okay? So there are my 4 coefficients. And now I can plug them in to construct the third degree approximating polynomial for this function. So it would be 1 plus 1/2 times x minus 1. Let me stop here for a second. This is the first degree approximating polynomial, which is just the equation of the tangent line, correct? This is a line. But I want to do better than that. So I want to do now, let's see. So I have negative 1/4 over 2 factorial times x minus 1 squared plus 3 over 8 over 3 factorial times x minus 1 cubed. So simplifying, my third degree polynomial will be 1 plus 1 over 2 times x minus 1 minus, this will be 1 over 8 times x minus 1 squared plus, and 3 factorial is 6, so the 6 and the 3 would cancel, leaving me with a 2. So let's see. 3, so it would be 1 over 16 x minus 1 cubed. Okay, so this is my third degree approximating polynomial. So that means if I wanted to approximate 1.06, right, I want to plug in 1.06 into this function. So this thing is approximately equal to 1 plus 1 half times 1.06 minus 1 minus 1/8 times 1.06 minus 1 squared plus 1 over 16 times 1.06 minus 1 cubed. And so evaluating this, I would get 1 half times 0.06 minus 1/8 times 0.06 squared plus 1 over 16 times 0.06 cubed. And so my value here is, let's see, let's put it in my calculator, 1 plus 0.06 divided by 2 minus 0.06 squared divided by 8 plus 0.06 cubed divided by 16. So we get 1.0295635. And that would be my approximate value for 1.06. So that's approximately equal to this. So if I plug it actually into the calculator, let's see what I get. 1.02953. So 1.0295635. So, that last digit way back there was wrong. But hey, it's a pretty good approximation. Okay, the moral of the story here is that, hey, this is how you find like an nth degree polynomial, right? You have to continually do these derivatives and plug in the value. So let's do an example where I actually do find the general term of the nth degree polynomial. So this is number 4 on worksheet 10.1, where I ask you to find the nth order or degree, whatever, Taylor polynomial for f of x equals ln of x, centered at a equals e. Okay, so again, start with the actual definition. So the nth degree polynomial, right, is the sum from k equals 0 to n of the kth derivative that would be evaluated at e over k factorial times x minus e to the k. So again, I have to find, if I'm asking for the nth order Taylor polynomial, you have to kind of find a general, right, there's going to be a pattern. You have to find a general expression in terms of k for this kth derivative at e divided by k factorial. So what I like to do is just start with, over here you can say, okay, here's when k equals 0, right? That's just the function itself. So k equals 0, f of x, that's the function ln of x, correct? In the middle column here, that'll be f of e, so that's ln of e, which is 1. And so what is f of e over 0 factorial? Well, that would be 1 over 1, which is 1. So again, the first term is 1. Now for k equals 1, that means I have to do the first derivative. The first derivative of ln is 1 over x. I'm going to write that as x to the negative 1 because I know I'm going to have to do the derivative at some point. So f prime of e, that would simply be e to the negative 1. And so f prime of e over 1 factorial, that is e to the negative 1 over 1, which is just e to the negative 1. This is my second term. Okay, continuing on. K equals 2, so put that in orange, be consistent here. So k equals 2, let's see, f double prime of x would be negative x to the negative 2. So f double prime of e is negative e to the negative 2. And so f double prime of e over 2 factorial, that would be negative e to the negative 2 over 2 factorial. Okay, I'm just going to leave it like that. I know 2 factorial is 2, but I'm going to leave it like this. Continuing on. I don't see a pattern yet. K equals 3. What do we have? We have f triple prime of x. That would be 2x to the negative 3. So f triple prime of e would be 2e to the negative 3. And so f triple prime of e over 3 factorial. that would be 2e to the negative 3 over 6, which is e to the negative 3 over 3. So there I did simplify, right? So why did I not simplify here, but I did simplify here? And why did I simplify here, but not here? Right, I'm trying to find a pattern. So I'm keeping them open. I know that this could have been 3 factorial, correct? But I also see that this 2 has canceled. So I'm kind of keeping my options open here to see what the actual pattern might be. So I still don't see anything yet. So if k equals 4, then I have the fourth derivative. So when I write the fourth derivative, I'll write a little 4 up there. This will be negative 3 times 2, x to the negative 4. So the fourth derivative at e would be negative 3 times 2, e to the negative 4. And so the fourth derivative of e over 4 factorial would be negative 3 times 2, e to the negative 4 over 4 times 3 times 2. So I get negative e to the negative 4 over 4. And so because the 2 and the 3 cancel, so I seem to see a pattern now. Anytime, except maybe saved for the first term, right? When k is 1, I get e to the negative 1 over 1. When k is 2, I get e to the negative 2 over 2. When k is 3, I get e to the negative 3 over 3. When k is 4, I get e to the negative 4 over 4. So if and also one thing to notice is that it does alternate, correct? So we have to be very careful there. All right, this thing does alternate after 1. Okay, so we may have to strip off this first term because it's not really following the same thing. So look at this. I could write Pn of x, the first couple current terms would be 1 plus e to the negative 1, x minus e, minus e to the negative 2 over 2, x minus e squared, plus e to the negative 3 over 3, x minus e cubed, minus e to the negative 4 over 4, x minus e to the 4th. Correct? So I'm going to leave this guy alone. So Pn of x would be 1 plus, and if I'm not mistaken, right, here I'll use blue now. If I look at these 4 terms, right, it almost seems like f to the kth derivative at e over k factorial is equal to negative 1 to the, let's see, k plus 1, because I want it to be positive first off, e to the negative k over k. So I can compile this into a series starting at 1 and going to n of negative 1 to the k plus 1 e to the negative k over k times x minus e to the k. So I've essentially compiled these infinite n terms there. And so this would be my nth degree Taylor polynomial. Okay, so this is kind of weird because that first term didn't really fit. But we can still just strip it off and write the series that way.